Swayam Prabha. Digital India. Educated India.
I just wanted to finish. So we've seen how to model elastically different defects. Now, once we have that, what do we do with it? And the main application is to use these eigenstrengths to compute elastic interactions between defects. And so how does that work? So I won't go into the math here, but you can show that if I have, so for example, imagine in my medium, I have a dislocation. So the dislocation will create a stress field at sigma 1 of R. And then I also suppose I have also a vacancy here that will create another. So it creates a stress field and a strain field. And here there's a stress field and there is a strain field. So now because elasticity is linear, the total stress field will be sum of the two. The total strain field will be the sum of the two minus their eigenstrengths. When you are inside here or inside the cut region here, you need to remove the eigenstrain of the. So the total energy, the total elastic energy of the system will be something like, so you have the 1/2, you have an integral over the volume, and then you have the total stress. So it's going to be sigma 1 plus sigma 2, double contracted with epsilon 1 minus epsilon 1 star plus epsilon 2 minus epsilon 2 star. You agree with that? Now I can expand, and what I'm going to get, I'm not going to go into all the details, but I'm going to get terms like sigma 1 double contracted with epsilon 1 minus epsilon 1 star. I thought, so if I start to expand, where the first term will be integral over V, and I have sigma 1 double contracted with epsilon 1 minus epsilon 1 star. The energy of the dislocation. Then I'm going to get an equivalent term, but with sigma 2, epsilon 2 minus epsilon 2 star. That's going to be the energy of the vacancy. And then I have all the cross terms. So I will have a term like sigma 1 double contracted with epsilon 2 minus epsilon 2 star, to the 1/2. And then I have another term which will be an integral of sigma 2, epsilon 1 now, minus epsilon 1 star. What we do, so this is actually exactly the same as that. Was that the stress field that the dislocation, because the elasticity is linear, the stress field that the dislocation creates, I mean, I can compute the stress field created by the dislocation without the solute. That would be sigma 1 and epsilon 1, as if the dislocation was completely alone. And then on the other side here, I can compute sigma 2 and epsilon 2 for the vacancy, as if there was no dislocations. Then I get the two, and both will interact through these terms. So it's not it's not because I sum the displacements, the strains and the stresses that they don't interact, because the energy will couple sigma 1 with epsilon 2 and sigma 2 with epsilon 1. So you had interactions even if the stresses are not affected by the presence of the second, or the stress of one defect is not affected by the presence of the second defect. That makes sense? So it's true that when you look at phonons, for example, phonons do not interact, but that's because the phonons are eigenstrains, and so they are perpendicular to one another. If you start to make a a linear combination, two linear combination of phonons, they might interact with one another, because if in the linear combination, the first linear combination, there's a phonon, and in the other linear combination, you find the same phonon, then these two will have an interaction term. You see, but it's because it's because you're using eigenvectors that are orthonormal one to the other, and not here. Is that so? Everybody is clear. So we have this big term here. So the math is a bit involved, and there is this nice website from Japan where guy, I don't know his name, but he has summarized all the microelasticity theory from Toshio Miura. So the Gori calculation is here. What you can show is that the sum of so first of all, you can show that this term is equal to that term. And then you can show that both terms are actually equal to, so this would be the E interaction. What you can show, and I don't want to do it on the board because it's too involved, but what you can show is that the E interaction is equal to minus the integral of the stress created by the first defect, double contracted, with the eigenstrain of the second defect. And this is the same as minus integral, the stress of the second defect, double contracted, with the strain of the first defect. I'm going to illustrate it. So I have the dislocation that creates sigma 1. I have the vacancy that creates sigma 2. If I want to compute the interaction energy between the dislocation and the defect, I have two choices. Either I compute the stress created by the dislocation on the vacancy, or I compute the stress created by the vacancy on the dislocation. No, they don't play any role here. The boundary conditions would change the expression, the exact expression of the sigma thing, but it's also true in an infinite medium. So you see, so for example, if this is okay, if you assume that this is a simple vacancy with an eigenstrain tensor delta V over 3V times identity. So that would be epsilon star 1. One way to compute the interaction energy between the dislocation and this is to use this first expression. So what will that expression be in this case? The E interaction will be minus. And so I want to integrate over the space, the stress field created by the dislocation, double contracted with the eigenstrain of the vacancy. Now the eigenstrain of the vacancy, it is 0 everywhere except at the vacancy, right? So what is this equal to? And inside the vacancy is constant. So it's going to be, so I take the matrix. So I have a matrix here, sigma 1 x blah, 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 sigma 2, no, sorry, sigma 1 y, blah, 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 and then sigma 1 z, okay? And I double contract with delta V over 3V times identity. And this is multiplied by V naught because this is non-zero over V naught, right? What is this equal to? Gonna be delta V naught. And this one, so in our notations, this would be V naught also. This would be the uniform volume of the vacancy. So I have a delta V naught times delta V over 3 V naught. Then the double contraction of this by that, it gives you the trace, right? It's going to be sigma Sx plus sigma Yy plus sigma Zz. That's the stress. That is the trace of the stress center. What is this, the trace of the stress center? Yeah? The stress hydrostatic pressure, this minus. So this is actually multiplied by minus, or it's three times pressure. The minus go away, the 3 go away, the V naught go away. What do I get? P delta V, which might be an expression that you have seen. The interaction of a dislocation with a solute, or is always, we say that interaction is P times delta V. This is coming from that directly. For a spherical object like this, we know what is the stress field. It's called the inclusion, the Eshelby inclusion problem. So I know what is the stress field created by a vacancy. And I could have I could have used the same thing, but looking at what is the integral of the stress created by the vacancy on the cut surface of the dislocation. And that would have given me exactly the same result. Except that you see that it might be less practical, although there's another expression for dislocations. But you see the idea. You can choose which one is the most convenient depending on your problem. We mentioned that in the seminar yesterday. A screw dislocation does not create pressure; it only creates shear. So a screw dislocation does not a perfectly straight, infinite screw dislocation does not interact with a center of traction or dilatation. Now there's this core region around the dislocation. If I'm looking at a solute inside the core region, and I can still use it mathematically, I can still use it, but it's going to be crap. It's going to give you just nothing realistic. Okay. Yeah, and then I'm not sure I want to do it, but there's this. So those who have done dislocations, you know the pitch color force, the force acting on a dislocation segment due to an applied stress. Actually, you can derive the pitch color force by applying just what we have written here. There's a little bit of math. I don't want to go into it. You can look at it for yourself, but you start from the expression that we have just discussed here, and in a few lines of calculation, you get the pitch color force. Because as we said, eigenstrain theory allows you to reconstruct completely the entire dislocation theory. So it's there. In one line, I can show you that the two terms are the same. Why? Because sigma 1, I can replace it. Sigma 1 is equal to C double contracted with epsilon 1 minus epsilon 1 star. And this is again double contracted with epsilon 2 minus epsilon 2 star. Now you can verify that it works. If I invert these two terms, this becomes sigma 2, and this is epsilon 1 minus epsilon 1 star. So this is this term. So in one line, I can remove this, and I can remove that. Now, what you need to show is that this integral here is actually 0 to arrive at the result. To do that, you have to, so the steps are, it's a bit like what we did initially. So you replace epsilon by its expression in terms of displacements, and then you do an integration by parts. And then through the integration, you find that there's one term which is 0 because of the boundary conditions, and the other term will involve the derivative of sigma, and it's the divergence of sigma, and it's 0 because of elastic equilibrium. And so both terms will go away, and you only keep this term. Yes. Yeah, because so when you do an integration by parts, the first term is an integral over the boundary of the system, and what you see is that integral here will involve either the displacements that are imposed on the surface or the forces. And so if you say that there is no stress, that it's the body globally is stress-free, that integral has to be 0, and it goes away. But again, now if you assume that you have applied a stress, you can either put the stress directly when you compute this integral, or more easily, you use superposition theorem, and you say that your stress body is the sum of the body with no stress plus the applied stress. And it's completely equivalent again. Am I making sense? Yeah. Does it more or less answer your question? It's look at if you want to have more details, it's fairly clearly explained in this webpage. Triaxiality. So it's not just a volume misfit, but there's a change in the shape. Then yeah, sure. Sorry. So if you have a change in the shape, so if it's a simple thing, it might be that, for example, here it's just tetragonal. So here instead of having 111, you would have three values: alpha, beta, gamma. And so it means that it will no longer be just the pressure. It's going to be, there'll be weights on the different elements. So it's going to be alpha times sigma XX plus beta times the sigma YY. It will just, you'll have a ponderation. You'll have weights on the different terms. So for those who are interested in eigenstrains, this afternoon so we'll see what we do this afternoon. Either we continue the dislocations or we do as expected, the third tutorial. In the third tutorial, one of the three subjects proposed is to get the eigenstrain of, I forgot what, maybe just a vacancy or something, but in iron or in another system as, for those who would like to see how it works. Whether the interactions are long range or not, all of these expressions, they apply. It's just the functional form. The form that will take the stresses of the strains will tell you whether it's long range or not. And then it's fine. And then if the integrals diverge, they diverge. And then you have to handle them by using cutoff radii or stuff like that. You have to be careful about the convergence of your integral. What is very interesting is, so I cannot, I could prove it, but I have to go through Fourier space. It's a bit messy. What is very interesting is, and that's one of the classical results of the H-L-B inclusion. If I look at the field, the stress field, which is produced by an H-L-B inclusion outside of the inclusion, does someone know what is special about the stress field outside of the H-L-B inclusion? For those who have already seen that, I don't know if anyone of you knows. Actually, it's a bit surprising that the stress field outside of initial B inclusion is only shear. There's no pressure produced by the solute outside of itself. It only creates shear and no pressure. So now the interaction of a shear is going to be the same as the P delta here. The interaction of a shear stress with another solute is zero. So actually, a field of centers of traction, of compression or dilatation, they do not interact with one another. They don't see each other. There's no interaction energy. And actually, you can push that result further. You can show that if you have any shape, so I take two regions that have diagonal, so they are centers of traction or dilatation. So both eigenstrains here are diagonal. Actually, both of them outside will create only shear stresses and they will not interact. So for example, because they don't interact, a shape like this or a shape like that, such that the sum of the two volumes here is the total volume there, these two, they have exactly the same energy. Because so it's called the Krummel something theorem. You can show that the energy of any distribution of diagonal eigenstrains, the energy is independent of the shape that you have. So in Fourier space, what you show is that the energy depends only on the Fourier term of the zero Fourier term. All the terms with a Q non-zero, they do not appear in the energy. And the non-zero Q terms describe the shape. But this one is not. The dislocation is not diagonal, right? Here in the end, what you get here, so you have other terms, but no, but what is special is that the edge dislocation creates a pressure field outside of the dislocation. So that pressure field interacts with the solutes. On the other hand, the solute outside of the solute does not create a pressure. It only creates shear. So there's no pressure term outside of a solute. due to a fluid. It's a surprising result, but this is an exact result from the HLB calculation. No. So if I did the same calculation here, what I would have is the stress tensor would have 0 here, and then they would have non-zero values here, and I would double that with 111. Or rather, it's not 0, but the sum is 0. This would be alpha minus alpha and 0, for example. Something where the trace is 0, but the terms are not 0. So the trace is 0. So when I double contract, I get 0. And so these two masses here, they will not interact. And so this has the same energy as that. So it means that when you have a Oswald ripening, do you know Oswald ripening? The fact that when you have precipitates and you let time go, the big ones will grow and the small ones will disappear. The driving force of Oswald ripening cannot be elasticity. If you assume that it's only a change of lattice parameter, it cannot be elasticity because the energy of big and small or bigger and no small, it's the same energy. It doesn't change because of that Krumel theorem. So it's only the interfacial energy that will drive Oswald ripening. Before the eigenstrain theory was formally developed, the first model of precipitate in an elastic matrix was developed by a guy called Eshelby, and he showed using elasticity. He found the expression for the displacements, stresses, and strains around a spherical or even an elliptical inclusion. And when we have a spherical inclusion, sometimes, I mean, we call it an Eshelby inclusion because it's the reference calculation. But what I've shown here is just a generalization of what he has done, and you recover exactly the same result as he has using what we have seen this morning. But it's just a name that we gave in the community, Eshelby inclusion. When you say in the community that you are looking at an Eshelby inclusion, people will already know that you're looking at a spherical precipitate with a volume misfit with the matrix. In the DD simulation, those who were at the seminar, in the DD simulations I showed in the second part of my talk, so I computed the interaction between a dislocation and solutes, right? Which side of the equation did I use yesterday? As on the dislocation. So in what I'm doing, in what I presented yesterday, what we do is we sum the stress fields due to all the solutes and look at what is the value at the dislocation. For those who have looked at Bill Curtin's models of solid solution modeling, and if among you some have looked at, what approach does he use? What side of the equation does he use? Okay, so he uses this expression, which is just the opposite. So Bill is on one side of the equation, and we are on the other side, but both are completely equivalent. So are you ready to talk about dislocations in crystals? I'll try to be brief, and I think most of you have already know already this. So I want to say, initially, we'll see how far we go, but I wanted to say the classical things about dislocations in FCC crystals, then go a bit faster for BCC dislocations, a bit faster for HCP, and even faster for dislocations in non-metals. But we'll see how far we go today. Yesterday, you have all been able to relax the edge dislocation in aluminum. What did you see when you relaxed the dislocation? So is the dissociation of dislocation in the CC crystals clear for everybody except probably for one of you? For the others, are you all familiar with FCC dislocations and the dissociation? So why does the dislocation dissociate? Yeah, we can do it by talking. All right. Because of French soil that we have seen. So here you have the so we take the case of an edge dislocation here. So this You have the line, you have the Burgers vector, and the dislocation will dissociate into two partials. And so the partials are of the type 1/6 of 112. And so what they do is they connect the 1/6 of 112, they connect the corners to the center of gravity. So you have two partials. You have A delta and delta B, and you have A delta and delta B. And in between, you have created the stacking fault. Now, the driving force is because if I look at the dot product of these two vectors, the dot product is positive. So the two dislocations repel one another. But as they move away, they create a stacking fault in between that keeps them together. And the equilibrium between these two terms gives you the dissociation distance. Is that clear? Now, in that drawing, I've put A delta to the right and delta B to the left. Why is it not delta B to the right and A delta to the left? Why did I do that and not A delta here and delta B here? Or is it just a choice that I did? Could I invert the two partials? Or no? No, imagine that, I take the same two partials, but instead of saying that this is this plus that, I can say that the same vector is that plus this. So I have an initial dislocation, which is like this, and there are two possibilities. It can do this, or it can do that. So if this is AD, and I have my triangle AD and delta, so that would be A delta plus delta B. That would be delta B plus A delta. Can I choose one or the other? Or so yesterday you saw, you think yesterday when you did the magnetization, some of you saw this and others saw that. I look at the cut surface and I assume that the cut surface is coming from the left. So this is my cut surface, and I need to say that the lines go in that direction, for example. Okay. Here I have two lips, right? And I have the S plus, which is towards us, and S minus, which will be on the other side, right? So the atoms that are here, how much have they been displaced or sheared? What's the this? So in this, so for example, assume that I have, for example, I initially, sorry, I'll do it in two steps. Imagine that for now I only have delta B coming from the left. The shift here will be equal to delta B, right? So I have delta B and delta B. Now imagine that I bring the second particle, which is A delta. The region here will be sheared by A delta plus delta B, right? So that's AB. And the region here is simply shifted by delta B. Now, let me draw quickly an SCC stacking. So we have the atoms in the first plane that are at the intersections. And then the second plane, for example, I put them at the center of the upward triangles. So imagine, actually I need a third plane. So the third plane would be these guys here. Now imagine that so the first plane would be below the shear plane. Now the second plane will be sheared by the Burgers vector. If I shear by AB, it's fine. These atoms, they will move from here to here, and so that's okay, right? What happens here? If I shear the second plane by delta B, what happens to the second plane? This is the second plane here. So this is the plane that I want to shift by delta B. And delta B is this guy here. So I take this atom and I move it by delta B, so it's going to go here. This one will go here. This one will go here, etc. What you have done is you have transformed if this is this is the A plane and this was the B plane. By shearing like this, by shifting like this, you have transformed the A plane into an A plane. So your stacking is going to be A, B, C, A, B, C. And that's not the stacking fault. Now, if we do the inverse, we do this. Now, in between, this doesn't change. In between, now I shear like A delta, because A delta is at the front, and this is delta B. And if I shear the second plane by A delta, I take this atom and I put it here, 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 etc. Now here I transform the B plane into the C plane, and so my stacking is going to be A, B, C, A, C, A, B, C, A, B, C. That's the stacking fault. So actually, you don't have the choice for the front, the first partial. The first partial is when you dissociate like this. The first partial is the one that transforms a plane in the stacking in the plane above. Because the other one will transform the stacking in the plane below, and that's putting atoms on top of one another, and that's energetically completely unfavorable. You see what I mean? So the simple rule that you'll find in some of the old books is that for this reference configuration, you put the Greek letter on the outside. You can do worse or more complicated, I don't know, because you have all seen the tungsten tetrahedron. So you bring me just one plane. But what we said is that in the SCC stacking, if I look at the three positions in one plane and the position in the plane above, it forms a perfect tetrahedron, and I can call the ABCD. I can call the submits ABCD, and then I call the centers of gravity opposite to a center to a summit. I call it with the corresponding Greek letters. So I have delta here. Here I have alpha. At the back I have beta, and then at the front here I have gamma. Yes. So what we say is that now we know that all the faces are 1-1-1 planes. So for example, imagine that I have one 1-1-1 plane here, and then I have another 1-1 plane there. And I'm going to look at an edge dislocation, which goes in this direction here, and it's going to be common to both planes. So I'm going to do this. And for the dislocation to be common, the Burgers vector would be the vector that has to be parallel to the intersection. So in our case here, that would be an AB dislocation. You see what I mean? So I have an AB dislocation, which is on this plane, and then it can also be on that plane because the Burgers vector is common to both planes. Now, we said, so this case here is the case that we have just looked at. So I know that there's going to be, no, wait a minute, what did I say? So AB will give me, A delta and delta B on this side. What is going to happen here? So here, so what are the partials on this plane? We can talk about the order afterwards, but there's going to be a dissociation into two partials. What are the two partials? So you can, it will be alpha, beta, or gamma. No, you can be more precise. You can be exact. You can tell me the two partials are. Well, the dissociation in that, so that plane here, sorry, maybe so that plane, that 1-1-1 plane here would be that face here, right? You see, I can try to do that. So if I'm looking at this space here, this is this plane here. And then the face, the bottom face here is this plane here. It's not really cross-slip. It's a dislocation that lives in two 111 planes. It forms, for example, as a result of a junction formation and breaking, for example. You can see many of them. I'll show you. We'll show you examples afterwards. It's a dislocation that lives in two different 111 planes. So what are the two in this red planes? The two partials are yes, I heard it. So gamma is the point. So it's A gamma or gamma B. Now, and that's the not sure. I mean, if you don't follow completely, it's fine. But so for this plane, when I'm looking at the dislocation like this, the top plane will be on this side and the bottom plane will be on that side. And I want to put first, or on this side, I want to put the partial that shifts a plane to the plane above. Now, I'm looking at this plane, and actually for me, the plane above is here. It's not this side, it's on the other side. And so the partial that we take a plane to the plane above, it's actually, so this one will take a plane to the plane below. So it's not this one that I want the other one. So on this side, because on this side, the dissociation will be, I said something wrong. It's the opposite. This one, I go from here to here, and this position is the position of the C-axis. So this one will take me to the plane below. That's not what I want. I want the other one. So actually on this side, I have gamma B. And on the other side, I have A gamma. So this is plasticity from the ACs maybe, but people at that time were saying that in this case, I'm looking at the triangle from above. I can see the tip when I'm looking here. And then when I look at the triangle from above, I put the Greek letters on the outside. Here, I'm looking at the triangle from one face. And when I'm looking at the triangle from one face, I put the Greek letters inside. It's technical, but I don't know. I did that a long time ago, but I always found fun this because now there's one more step, which is that you know that the Burgers vector has to be continuous, constant along the line. So here, if I have a Burgers vector A delta here, and I have a Burgers vector gamma B here, it is not possible unless there's another dislocation here that connects this node with that node. For example, in this direction. And now I have like an electric circuit. I have a Burgers vector coming in. I have a Burgers vector coming out, or I can put it in the other direction. I have a Burgers vector coming in. I have a Burgers vector coming out. The sum, and then I have another Burgers vector here coming out. So for the topology, what I need to have is the sum of the three Burgers vectors has to be 0. Yes? And so the Burgers vector that I have here is a nasty Burgers vector. It's going to be gamma B minus A delta. So it's a weird vector because it is gamma B. Gamma B, it's this vector here. I'm putting blue. It's this vector minus A delta, which is the vector at the back here. So it's a long Burgers vector, right? It's a long vector. So this segment here has quite a bit of energy. So what is going to happen if this is very expensive? What is going to happen near here? What do you think is going to happen? The system will try to have this segment as short as possible. And so the structure that you will have is actually not that. The structure that you will see is this. To keep that segment as small as possible. You told me you knew the FCC dislocation, so I thought, I could go full stream with you, but okay. So this we have seen. This was to explain why it's the A delta partial, which is at the front. No, this we can come back to it. This is the calculation for the equilibrium distance. So that's what we said together. The total energy, there's a term here which is a recursive term, the two dislocations that want to move away, and then there's the surface energy that keeps them. You minimize that and you find what is the equilibrium distance, the dissociation distance. What is interesting is that the dissociation distance obviously depends on the stacking fault energy, but not just on the stacking fault energy. It also depends on an elastic term, which is mu b. So interesting here, I mean, aluminum is known to have the smallest dissociation distance, but it's not the material that has the highest stacking fault energy. If you look at these data here, I look at aluminum, it's stacking fault, it has the highest, but where is the inversion? No, it's between nickel and copper. Sorry, no, aluminum has a high stacking fault energy, and then these are its elastic properties. And so this factor here is 30. You take nickel; it has a lower stacking fault energy, higher elastic constants. It gives you 85. I'm not sure it works here. No, I thought there was an inversion. Anyway, I thought there was an inversion. Maybe there's something wrong in what I've written here. Anyway, so the main thing is that so you have both elasticity and stacking fault that play a role. Now this is the first slide on these reactions. So these dislocations here, because they are at the junction between two different planes, they are called stair rod dislocations because of these old staircases where you had the carpet on the staircase, and then they would put a rod to stick the carpet to the stair. Yeah. So it's called, these rods are called stair rods, and this is reminding of them here. So you have a number of stair rod vectors. And you can see all of them here in the Thomson tetrahedron. So we have seen one which is of a large amplitude, which is A gamma minus B delta. There's one which is very short. So now you have other things. For example, you can join gamma with delta. You see this vector here? This is another stair rod. And this is very short segment. It's called a Lomer-Cottrell partial. And this is the smallest you can find. And this one is very energetically favorable. And then you can form others, right? And now these segments, these stair rods, they occur. So in the example I took here, the other very classical example is the so-called Lomer-Cottrell lock, where you have two dissociated dislocations on different planes, on different 1-1-1 planes. They come in contact. And because of the difference in the dissociation here, what forms here is a Lomer-Cottrell lock. So it's this very short dislocation segment that forms along the intersection line. And because it's of low energy, this is a strong pinning point for both dislocations. You have that. There's cross-tape. We can talk about it later. And then there's the so-called stacking fault tetrahedra, where if you form in SCC, if you form a vacancy loop with a triangular shape, all of the edges, they can dissociate, and by magic, when you look at all the dissociations, it only creates on every side of this triangle with the dissociation and reconstruction, you only form Lomer-Cottrell segments. And that induces this segment to dissociate and go up along the 1-1-1 plane, and it forms a tetrahedron where you have stacking faults on every face, and you have a Lomer-Cottrell locks or rods on every side of that triangle. So it's a very stable vacancy defect that you see with irradiations, for example. I can show you, but again, I can do some archaeology. Let me show you. It's good. I revisit my old paper. There is there's this one, for example. So this is work from 05. Are you born in 05? I don't want to know the answer. Anyway. So in this paper, yeah, so we did, this was MD back in the days. By hand, we created these stacking. So these are stacking fault tetrahedra. So we created triangular vacancy loops. We let them relax and they form these tetrahedra. So in gray here, you have stacking faults, and then the edges here are the Lomer-Cottrell blocks. And then in the same simulation, we add a dislocation, and then we apply a stress to force the dislocation to interact with the stacking fault tetrahedra and see what happens. And in some cases, as you can see here, for example, the dislocation is able to absorb. So this is still full of vacancies. So when the dislocation comes, it interacts, and in some cases, it can absorb the vacancies, and it locally finds when you form these double jaws. In other cases, it just cuts the stacking fault tetrahedra with different types of reactions. But these were simulations from the old days. And these are, we were doing this because the stacking fault tetrahedra are some of the very classical irradiation defects that are created in some SCC materials, in particular copper. Yes, am I making sense? Yeah. Okay, I can see that, there's the SCCT killed you. So I'm going to go through the slides as been stating now. So again, archaeology. So now we are in 2000. So I'm sure none of you were born. That's fine. So these are, really old calculations. This is an edge dislocation, and it has absorbed, and actually in this case, it's an interstitial loop. And so you have segments in different 1-1-1 planes, and then you can play the game of connecting all of the stair rods. So this is so you have the two main Shockley partials on both sides here, but on this side you want to form one of these very long Burgers vector stair rod. So actually it constricts. On the other side you form a Lomer-Cottrell. So on this side it is extended because this is of low energy. Then you have another Lomer-Cottrell here, and then you have another large Burgers vector stair rod at the bottom here, and then you have stacking faults everywhere. So there are a lot of game to play with these partial dislocations. If I call this X, so what I have is X is gamma B minus A delta. I can say this is gamma delta plus delta B minus A gamma minus gamma delta. So the two gamma deltas go away. I have the delta B, which is here, minus the A gamma, which is there. So it works. They both, so their Burgers vectors being like this, they can both move in their plane. And so that segment will move along the intersection. Okay, so I said that I wanted to say some detailed things about SCC. I'm going to go faster with BCC. Yes? No, sure. Yes, so that's, sure. The equilibrium, so if there was no line tension, the segment here, because it's big, it would be completely zero. But to be completely zero, you have a large price to pay. And so there's an equilibrium between the line tension of the dislocations there. So it's not necessarily exactly zero. It would be much more than the other one, but it will not be exactly zero. Okay, so quickly for BCC, so in FCC, the stacking fault is a metastable state. In BCC, there is no such stacking fault. If you look at how the energy varies when you shear a crystal. In FCC, you would have the metastable stacking fault. You would have something like this with an intermediate metastable state, which is the stacking fault. You do the same in BCC. Whatever the plane you do, you always have a single maximum. There's no metastable stacking fault in the BCC structure. As a result, the core of the dislocations are not dissociated. At most, they can be extended. Although I argued yesterday that the extended core is an artifact of the interatomic potentials, but it can still be a little bit extended, but it's not going to be dissociated. And then the other particularity, but we're going to talk about that more when we talk about mobility of defects, is the fact that these screw dislocations have a high pile stress. I want to go into more detail. Actually, this is only what I want to do about DCC. So HCP is site defense. That's what I want to talk about. So HCP is the nightmare, right? You all know, and we have argued about that. So first of all, so even if I look only at a Burgers vector, so one side of the hexagon here, that Burgers vector can be associated with dislocations that glide either on the basal plane, the prismatic plane, but also the pyramidal 1 plane, pyramidal 2 plane. When you take the same screw dislocation and you relax it in the different planes, you get different core structures. Now, in the basal plane, as well as in the prismatic plane here, there is a stacking fault. And so there is a dissociation. It's not the same as here because here it's the A Burgers vector dissociates into A over 2 plus A over 2. They move away and they live in between a stacking fault. But it's of a rather high energy, so the dissociation is always quite small, right? And then you have more complex core structure that involve nanotwinning in these other. Sorry, this one is the prismatic. And now in some HCP metals, plasticity is mostly on the basal plane. An example, the classical example of magnesium. In others, the plasticity is mostly on the prismatic plane. Titanium. Why is that? Yeah, or yes, but in terms of stacking faults, in magnesium, the stacking fault in the basal plane is smaller than in the prismatic plane. And so the dislocations preferentially dissociate on the basal plane. And once they're dissociated on the basal plane, they move on the basal plane. So titanium is a bit weird. It's more like zirconium, for example. Zirconium is quite clear. In zirconium, it's the opposite. The stacking fault in the prismatic plane is lower than in the basal plane. Dislocation is dissociated on the prismatic plane, and they move on the prismatic plane. If I'm correct, right? Titanium, there's something about titanium. And just to finish, so these were calculations done by Dave Sorovitz with neural network potential, DeepND potential. These are DFT calculations to compute the stacking faults with or without solute elements. I took it from this paper here back from 9 years ago. What you see is, for example, so it's a bit involved, but this is the generalized stacking fault on a prismatic plane, and the black curve is in pure titanium. And you see that when you are here, there's a metastable state in between. That's the prismatic stacking fault. If you do the same in basal, you are here and you have the same thing, the stacking fault in the basal plane, which is here. Now, when you add solutes, it can completely change. So, for example, here, if you add SN, tin, you see that adding tin near the stacking fault can completely remove the metastable state. But adding at a different position, it will keep the stacking fault but make it higher. So there's a lot of alloying effects on the stacking fault. You see you see the two stacking faults in these planes. The rest is the same. It's just a variation with the different elements. Am I making sense? No, actually, I'm wrong. Sorry. This is prismatic and this is basal. But it's the same idea. In basal, you also have stacking fault. So this is titanium. We said, so the fault in the basal plate is 0.3 something, and it's 0.2 in the prismatic plane. So it's lower in the prismatic plane than in the basal plane. So is that clear? Now, just one quick word for those who are not looking at metals. We haven't talked much about non-metallic systems. So in particular, if you want to look at ionic systems, so the first thing we've already said that we need to use dipoles or quadruples. of dislocations to avoid free surfaces, because free surfaces will be charged and that will create interactions with the dislocations that we want to avoid. So the first thing is you always work with early boundary conditions, in this case, a dipole. Then you have these Coulombic interactions. The classical way to account for these is to do what is called an Ewald summation. It allows us to account for the long-range interactions, the long-range Coulombic interactions, but it's very computationally expensive. What people do more and more nowadays is to use a cutoff radius, as with other potentials, but big enough such that locally you can account for the ionic interactions. And it has been shown many times that actually even using a cutoff radius can really replace the Ewald summation, but for computing time, which is much smaller. So more and more people do that, and it's called the Wolf computation. Now, because these non-metals are always compounds and with charged particles, you get a whole variety of Burgers vectors, slip planes, and core types that can be charged or neutral. So same thing this afternoon. There's one of the exercises is on UO2. So I've worked few years back. We work on oxide uranium, and this is an example of the 5 different core structure that you can get in oxide uranium for exactly the same dislocation. So it's an edge dislocation. In this, so this is your uranium oxide has a fluorite structure. The Burgers vector is 1/2 of 110, like in SEC. But the glide plane is also a 001. So here we are looking at always the same edge dislocation within 1/2 of 110 Burgers vector, 110 plane. Depending on the initial configuration, how we have arranged the atoms, we can either have a charge cores. So here there's a missing oxygen atom. This one has an extra oxygen atom. So one is charged negatively, negatively, and the other one is charged positively. Or you can have neutral cores that can be either symmetrical or asymmetrical or in zigzag along the dislocation line. All of these are possible. They are all metastable. Usually the charged cores cost much more energy than the neutral cores. And in the case of the of oxide uranium, the most stable, I mean, in DFT, this core is the most stable. This one is close by. This one is more expensive, with depending on the potential. So we used an empirical potential for these calculations. Actually, this one was of lower energy than that one. Let me remember. There was something with the interaction of the oxygen atoms with the rest. So when you break the symmetry, you make this oxygen atom closer to that one, but further to the other one. And in the end, it costs less Coulombic energy than having it at equal distance between the two first neighbors. Or we had some argument to explain why it's asymmetrical. Yes, definitely. The core structure is even more sensitive to chemistry than in the metals. Yes. And the stability of these, as I said, the stability of these different cores really depend on the type of potential that you are. So HCP is a nightmare among metals, but there's an even worse nightmare when you go and look at non-metallic. Okay, I'm done. So we have the tutorial this afternoon, just since we left early. Yesterday, so you all got the dissociated edge dislocation. Yes, this one worked. Who has been able to go? The question is whether we continue on dislocations this afternoon. We continue the tutorial from yesterday, or if we move to the next one, because we could shift everything and then do a tutorial on Friday morning. It's a bit up. It's a bit up to you. Yeah. So how far have you been? So I forgot what was the next step. Is it? Yeah, J2. So the first step was the perfect edge dislocation. Dislocation loop. Yes, some of you have done, and you have. You too? Who else has done the dislocation? You too? And then the next one, the screw dislocation. You thought, so Luke is the furthest you've been, or you've done the screw dislocation? So, I don't know, do you want to continue this afternoon? Do you want to continue looking at dislocations? Yes? We continue, you look at least at the screw dislocation to see how it's different. Maybe you could also use, instead of aluminum, you could use copper, for example, where you have a much larger dislocation, with the edge and the screw dislocation in copper, and then you will see the difference in the dislocation bit. Right? No, it's up to you. So if someone want to continue working on dislocations, you can, or you can move to the third tutorial also if you want. And so for today, since I didn't know really, where you were coming from, what were your interests, what I thought for today, the third day, was to propose 3 different exercises, and you can do just one, you can do several. So one is, so the first exercise is on a grain boundary. And so it's I took it from a PRL paper that happens to be written by some of my friends. There's this shear coupled motion, which is that you have a grain boundary, and you shear the crystal with the grain boundary, and what you see is that the grain boundary actually moves because you are shearing the crystal. The grain boundary will go either up and down depending on the shear. So this is an interesting exercise because first it shows you how you can use atom scale to create a grain boundary for those who are interested in grain boundaries, and then you can run a quasi-static simulation where you shear the system and see when and how the grain boundary moves. The second example is, I didn't give much details, but you have the input scripts if you want to look at them. I think you have all the ingredients to, on your own, create an edge dislocation in UO2. So get one of the cores that we just saw. I think you have everything. I give you how to create the potential. That's the main part, is how to create that ionic potential. But this is explained here. And then create the dipole and then relax the dipole. And for those who don't feel like doing it on their own, I've in the folder you have all the solutions to do. And the last example is related to what we talked about this morning, is to compute the eigenstrain of a vacancy and the activation volume or relaxation volume. And I think, and this is in, actually, this is exactly what I showed you this morning, that just you do it yourself. What is proposed here is just a vacancy in aluminum, as you have seen this morning, but just for you to make sure that you can reproduce what I've done. And interstitials, you mean, or interactions? Here is so what I call the volume relaxation is it's the activation volume. So it's V naught times the eigenstrain tensor, which is the quantity which is well defined, which is the quantity actually that you compute first before you get the eigenstrain. It's just to give you an idea, and then so here this is wrong. So this is certainly not UO2. It must be eigenstrain. Sorry, small typo, but now you know that there are typos everywhere in what I did. So same in eigenstrain, you have all the scripts that you need to compute these eigenstrains. So I guess it's really up to you. Those who want to do dislocations, continue doing dislocations. Those who want to look at one or two of these examples, go for it. Okay, this is completely correlated. I'm just trying to think about how I can explain that. So what we said, so the activation volume we said is the volume of the inclusion times its eigenstrain tensor. We have also seen that but if I apply shear stress to the system, the interaction energy or the effect of the shear stress on that defect will be the stress tensor contracted with this term here, right? If I take a dislocation, for example, and this eigenstrain tensor will be Berger's vector dyadic product times n times the delta function of R belonging to S. If I do all the different products, what I am going to get here, let me not say something. So yeah, you have to be careful because the dislocation, the volume is, it's a platelet. But in the end, what you are going to get as an activation volume will be the result shear stress. It would be only the result shear stress left because of this dyadic product, multiplied by B, multiplied by the surface is the dislocation gas. So the activation volume usually is given by this term here. This is the surface swept by the dislocation as it moves, multiplied by its Berger's vector. So this is a physical volume because it's related to the surface swept by the dislocation. For other defects, like for a vacancy, it will be for the vacancy. What I'm going to get here is this P delta V that we talked about, and that will tell me what is the effect of an applied stress on the energy of the vacancy, and the activation volume will be. Yeah, is it really physical? It's not really physical because this is a mixture. This is a mixture of the volume, the relative variation of the volume of the vacancy multiplied by its volume itself. So this would be the initial volume of the vacancy, and this would be the strain, the eigenstrain related to the vacancy itself. So the activation volume is not here. It's a product of both the eigenstrain and the initial volume. And it's basically what is the difference between the volume that the vacancy would like to have compared to the volume it has before relaxation. So it's a relaxation volume in the sense that it's the change of volume that will have the vacancy as it moves, as it evolves from its initial configuration where it has the volume in the matrix to the volume it would like to have. So usually it doesn't go that far. That's physically the meaning. With dislocations, the activation volume is related to how much the dislocation will bend before it can unbend. So if you have a small activation volume, it means that the dislocation does not bend much before it unbends. High activation volume means large bending. So it has to do with the density of defects, but also it has to do with the strength, the peeling strength of the defects. Yeah, we hadn't talked about the Frank partial. So yeah, the Frank partial is this one here. So it is along 111, and it forms with irradiation defects mostly. But for me, the Frank partial is only seen as a result of irradiations. And this Frank partial can decompose into this partial plus that partial also. So you can have a decomposition of the Frank partial. So again, I can use some archaeology if you want to see some old simulations. I think no. Okay. Because we looked at back in the day we looked at the interaction of dislocations with Frank loops, and we saw these reactions induced by the interaction. I can show you. I just need to find which MD on. So 04, so maybe some of you were born. And by the way, this is a paper where we first proposed these shifts for the screw dislocation. And yeah, so here, for example, this is this dislocation, this loop, hexagonal loop here. This is an interstitial loop. So by hand, we added the extra atoms in the structure. We let it relax. And it has exactly this Burgers vector, this delta B Burgers vector. There's a Frank Burgers vector, and this is a screw dislocation that comes in contact with the loop. And because it's a screw dislocation, when the dislocation reacts with the loop, it cannot climb because it's a screw dislocation. So what it forms is what is called a helical turn. It forms a structure which is three-dimensional. I think is there a three-dimensional picture somewhere? Yes, I have here 3D. So the screw dislocation, after it has absorbed the loop, actually now lives on different slip planes and forms a three-dimensional structure that looks like a helix. So this is why it's called a helical turn. This is something, again, you see these helical turns when you do microscopy after deformation on FCC irradiated materials. But Frank loops are, only, I hope I'm not saying something wrong. I think it's only seen under irradiation. In brain samples? Yeah. Right. No, I remember that it was also the points for high temperature, from high temperatures. All right, thanks. Yeah.